In this video, we are going to specifically calculate heat values that accompany a chemical reaction. So the broad topic for that is thermochemistry. In the previous slide, we looked at the 3 laws of thermodynamics, and the first law of thermodynamics, stated in a sentence, is energy cannot be created or destroyed. So there's a lot of ways of saying that. Mathematically, we will write E for energy is Q plus W. Q is heat and W is work. So energy units that we're going to use are joules. So we might see a joule or a kilojoule. And if you've had physics, you know that a joule, or work, for example, is a force in newtons times a distance in meters. So again, we are not going to look at the work term, because unless a distance is traveled, then the work term is 0. So if we have a gas that's expanding in a cylinder, for example, and causing a piston to move up and down, then we would have a work term. But if we're just doing tabletop chemistry, where reactions are occurring and there is no gas that's expanding, then we're going to simplify the first law of thermodynamics into the energy is approximately the same as the heat. And once again, if the heat change occurs at a constant pressure, then we get to call Q a capital state function variable H. So that just means heat. Okay. So delta is going to be the term we use to take the difference. So capital Greek letter delta kind of is like our word difference, so we'll use that. That is always going to be final minus initial. So for chemistry, that's going to mean products minus reactants. And a very important concept is a negative value. So if we have a negative delta H, that means that the delta H value is less than 0. Then we have an exothermic reaction. So heat exits the system, or we could say heat is produced. So this is definitely favorable as far as the universe goes. The universe likes to go downhill in energy. If the H value, or the difference in the two states, or the products minus reactants, if that's a positive number, that means we have to add heat to the system, or that the system absorbs heat. So we could either add heat by using a propane burner, or our body could be used. So the reaction might just naturally absorb heat. So this, for example, would be an ice pack. So if you go to the store and buy an ice pack, and you crack the ice pack and put it on your arm, that chemical reaction that's occurring inside the ice pack is actually going to pull heat out of your body. So again, most equations have a negative delta H value because that's the way the universe goes, is downhill in energy. So we are going to look at a chemical equation. This is kind of hard to see, but that says CH4, that's methane. Methane's the simplest hydrocarbon. Methane is a fuel. It will burn in the presence of oxygen and make carbon dioxide and 2 moles of water. And the heat that accompanies this process has already been determined to be that value. These are the states. That's a gas. Methane's a gas, oxygen's a gas, carbon dioxide's a gas, and water in the liquid state is generally produced in a combustion reaction. So 1 out of 3 different ways that we're going to do calculations with delta H is when the heat term is part of the balanced equation. So we may see questions like asking us for the mass of a reactant or product, and it might be giving us a certain amount of heat. So if we think of just using the balanced equation, 1 mole of methane will always produce 890 kilojoules of heat. So if I double this, if I have twice as much fuel, I'm going to have twice as much heat generated. So that should make sense logically. So if we are given a question that has a heat value in it, then we'll just start with that number and the unit, kilojoules. And I love the science of canceling units, so I'm going to always do that. So that unit kilojoule, it has to cancel a unit kilojoule, and I'm going to use this value from the exact balanced equation with that heat value that would accompany that. So the negative 890, since we're calculating a mass, that the mass number can't be negative, but that amount of heat accompanies 1 mole of methane, so that 1 is not written, but that is part of the balanced equation. Okay, so we just treat that value just like it was part of the recipe because it is. And kilojoules cancel. And if I read the question, I'm looking for mass of methane, so I've got to get out the periodic table and use the molar mass. So I add up what 1 mole of each atom weighs. So 1 mole of CH4, it's going to be carbon, weighs 12, so we're going to need this calculator anyway. 12.01 plus, there's 4 hydrogens, 4 times 1.008, and when I do that I get the mass of the compound, so 16.042 grams of methane for every 1 mole of methane. So our moles cancel, and the unit that my answer will be in will be grams. So that 16 is already in the calculator. I'm going to divide that by 890 and multiply by 2550. And if I did that right, that's 45.96. So if we are considering significant figures, here we've only got 2. So we'll just round this answer to 46 grams of CH4. So this should be similar to what we've done in previous chapters, where we might go from mass of one formula to the mass of another. So the balanced equation step is always part of that process. Okay? So we'll work this a different way in the next example. We might be asked to calculate a heat value for a specific balanced equation, and the problem may give us a mass number. So if we look at this question, it's still pertaining to the combustion reaction above, so from the combustion of methane. This 1 mole of methane is going to make 2 moles of water and give off that much heat. So the two, now what I'm going to care about for the balanced equation are those 2 values. So my mass of water is given in kilograms. Molar mass is always the mass in grams of 1 mole. So I've got to turn 25 kilograms into grams. So that would be 25,000 grams of water. And then if we're given grams, most likely we're going to convert to moles. So grams of water per 1 mole of water. So if we add an oxygen to 2 hydrogens, using the atomic masses, we'll come up with 18.016 grams of water per 1 mole. So our grams of water cancels. And now this specific recipe, 2 moles of water generated will accompany that much energy. So that is really our balanced equation step. So 2, that 2 comes from that 2 there, 2 moles of water with that much heat, and we could write it as negative. The negative sign here is just going to mean that much heat is released. Oops. So if we make sure our units cancel, moles of water cancels moles of water. I'm going to start with 2,500 and just plug all those in. 2,500, 25,000, I'm sorry, 25,000 divided by 18.016 times 890. That's a big number. So this would be negative 1, 2, I'm going to fill those in with zeros. 1, 2, 3, 4, 5. And that's correct. So we might change this to, we might change that to scientific notation. It's already in kilojoules. So we might say 1.2 times 10 to the 1, 2, 3, 4, 5, 6 kilojoules. So the negative sign just means that that is energy that will be released by this chemical reaction. Okay. So if we're given mass, we're going to convert to moles of whatever the substance is given, and then to convert to the energy value, we're going to use the balanced equation for that. The other type of calculation, or another way we could come up with the same value, is use the appendix in the back of the book. So the heats of formation, I forgot the little circle there. The heat of formation given for any substance in the back of the book is the formation of 1 mole from the elements. So we're going to look at the appendix and we'll see that if we have elements listed, the way oxygen occurs in nature is the diatomic molecule as a gas, we're going to see that the delta H value, the formation for that, is going to be 0. So we're defining elements to be 0. I'm going to rewrite the equation above so we've got something to look at. So when 1 mole of methane, the gas, reacts with 2 moles of oxygen, so it would require 2 moles of oxygen gas, and then that will produce 1 mole of carbon dioxide in the gas phase and 2 moles of water in the liquid phase. So the textbook back of your general chemistry textbook or the CRC handbook of chemistry and physics will have these delta H values listed. So I'm going to show the back of this textbook, and we're going to find CH4 from the book. So CH4 gas, the first column gives us the delta H values, so that is a negative 74.8, and the units for those values given are in kilojoules per mole. S is the second law and the third law of thermodynamics, that entropy term we talked about on the previous slide, and delta G, that's free energy, so we're not going to care about the second and third columns. So if I look over to CO2 in the gas phase, CO2 gas has a value of negative 393.5. So I'm going to write those two values right here under this. That was negative 74.8. 74.8. The CO2 value was negative 393.5. And the liquid water, we have to be careful when we look at that. We've got to look at the correct physical state. So water in the liquid phase, oh, that looks terrible. It's not focused very well. See if we can bring that into focus a little better. So water in the liquid phase has a value of negative 285.83. In the gas phase, it's a slightly larger number. It's less negative. So we want to make sure that we get the right state that something's in. And while we're here, we'll look at oxygen. The element oxygen, if we forget that it is an element, we'll see that the heat of formation will be 0 because this is the way oxygen occurs at normal conditions. 25 degrees Celsius, 1 atmosphere pressure. Okay, so we'll use negative 285.83. And I just have to write that down so that I don't get confused. Okay, so what we're going to do here is take products minus reactants. Okay, so that is the second case of calculating the delta H values. When we use values from the back of the book. So that delta always means final minus initial. So we have to subtract in the correct order to get the sign correct. So if our sign's wrong, that's a very different situation. So a negative delta H is not the same as a positive delta H. So we want to be careful about that. So if we go back to this balanced equation, there are 2 water molecules, so I could put 2 moles of water and then multiply that by this value, negative 285.83 kilojoules per mole. So that's going to cancel anyway, the mole unit. And I'm going to add that to the delta H value for carbon dioxide. So that is 1 mole of CO2 multiplied by negative 393.5 kilojoules per mole. Then I'm going to subtract from that the sum of the delta H values for the reactants. So in this case, we don't have to worry about the minus sign. We're only going to have 1 reactant. We've got to be careful about that. So I'm going to subtract from that, and that's a negative 74.8. And there's only 1 mole of that, so I'm not showing the kilojoule per mole. I should show that cancellation to be consistent. And then I would also subtract from that the value for oxygen, 2 moles of O2, but that value from the back of the book is 0 anyway. So we want to make sure that we always subtract off all the reactants from the sum of all the products. And then getting that entered in the calculator correctly, because almost every value for the compounds are going to be negative because that's what nature likes. So negative delta H values are common. Just have to be careful. 2 times negative 285.83 plus a negative, or we could just put minus 393.5, and then minus a negative, I'm going to put plus right there, plus 74.8. And if we do that, then we'll get the same value. It's not focusing very well. We'll get the same value that the book gave us, or the same value that we saw from the reaction above. So I'm just going to write that down. So delta H for this reaction is negative 890.36 kilojoules. And that is the value that was given in our initial example. So these values for heat that accompany any balanced reaction, these can't be made up by the teacher. We know for any chemical reaction, as long as we know the delta H values for that formula listed in the back of the book, then we can calculate that. So the fact that we were given this amount and the fact that we calculated that same amount is not a coincidence. So if we have a good author of a textbook, they'll make sure that every balanced equation will have the correct value for the heat that would be exchanged during that process. So if we do one more, this would be an example. This is when iron rusts. So the chemical formula for rust is Fe2O3. So if we have iron, if we look in the back of the book at iron in the solid state, its delta H value is 0 because that's an element. And we saw the delta H value for oxygen, that is also 0. And the value for Fe2O3 in the solid state is right here, and that's not going to focus very well. Keep adjusting this. There we go. So we see that right here, 822.16, and that's a negative value. So again, we have to pay attention to the state and the formula, negative 822.16. All right, let me get this back. I focused a little better. So this value was negative 822.16. So if we're going to calculate the delta H for this reaction, we're going to have to take 2 times that value, because there's 2 moles, 2 times negative 822.16, and we would subtract off 4 times 0, which of course is going to be 0, and we would subtract off another 3 times 0. So the reactants aren't always 0, but if any formula that is an element, we'll see that those values are 0. So we just multiply this by 2. So the heat for this reaction would be negative 1644.32 kilojoules. And then a question that I like to ask so that we get the vocabulary down right is, could this heat of reaction represent the heat of formation for iron 3 oxide? So the delta H circle formation means we're forming 1 mole. So I'm going to exaggerate this 1 over here. And we wouldn't see that written anyway. So if I cut this recipe in half, then I will have a heat of formation value. So we may see fractions now as coefficients. And so I'm going to run out of room here. So I'm not going to try to squeeze in the states. But exactly half of this recipe, then if we look in the back of the book, the heat formed for this reaction would be the negative 822.16 kilojoules. So the point of asking this question is to reinforce the definition of what delta H little circle F means that's the formation of 1 mole of a compound from the elements. The last way we're going to calculate delta H is with a puzzle, sort of, and that is using Hess's law, so we'll look at that on another video.